Okay, let us start with the last chapter of this course, which will be organometallic reactions and catalysis. So thus far we have looked at selected classes of organometallic compounds. Now we are going to look at what reactions these organometallic complexes can undergo. In particular, we will look at applications on organometallic reactions in catalysis, which has many practical applications. So firstly, we will look at reactions that are associated with the gain or loss of a ligand. So firstly, there's the ligand substitution, and that kind of reaction we have already looked at, so we will not look at that much further. Secondly, and that will be a new reaction, that will be the oxidative addition. Then the reverse of the oxidative addition, which is the reductive elimination. And finally, the nucleophilic displacement. So these reactions are associated with a potential change in coordination number. That's different to the ligand substitution reaction, where there is usually, or there's actually never a change in coordination number, because you only substitute one ligand by another. Okay, now there's a second type of reaction that we will discuss, and these are reactions involving modification of ligands. And these reactions will be migratory insertion, and that is a reaction between a neutral unsaturated ligand and an anionic ligand. So the neutral ligand actually inserts into the anionic ligand to give a larger ligand, and that will be the B-hydride elimination as a second reaction. So first of all, let's look at the oxidative addition. So an oxidative addition is a reaction in which one or more ligands are added to the metal of a complex and at the same time oxidizes it. So are different types of oxidative additions. So one is a cis addition and a trans addition. Secondly, there can be so-called mono and dinuclear oxidative additions. So let us look at first at the mononuclear cis addition. So here's a reaction that is such a mononuclear cis addition. You see here a chloro bis triphenylphosphine carbonyl iridium complex. So this is a square planar complex because here the iridium is the oxidation number 1. And when we add H2 to this ligand, then this H2 adds to the complex, thereby increasing the coordination number from 4 to 6, whereby the two hydroligands stand in cis orientation to each other. Okay, so we are going from the coordination number 4 to the coordination number 6. So what is the oxidation state? Well, I said previously, this here is iridium 1. We can easily verify this by electron counting. So the iridium has 9 electrons. When we use the neutral atom method, the chlorine adds 1, and that's 10 then, and the 2 phosphines at 2 each, so that's 14. And then there is a carbonyl in addition, and that makes 16 electrons. So how do we get, that's the electron counting, but how do we get to the oxidation state? Well, the carbonyl is neutral, the phosphines are neutral, but the chloroligand is anionic. So overall, the complex is neutral, and therefore the iridium must have the oxidation number +1. So over here, the iridium has the oxidation number +3. How can we see this? Well, again, the phosphine ligands are neutral. The carbonyl ligand is also neutral. But the two hydrido ligands are now counting as anionic ligands. And the chloroligand is again anionic. So again, overall, the complex is neutral. For that reason, the iridium must have the oxidation number +3. So that means that we really have an oxidation here from iridium 1 to iridium 3. Okay, so let us go to a second example where we have a mononuclear trans addition. So we again start out here with the iridium complex, but now we add methyl bromide. And now that methyl bromide adds in a trans way. So that means that the CH3 group and the bromo group are in trans position relative to each other. So why is this an oxidative addition? Well, obviously we have added ligands here, but the oxidation number goes up from, again, +1 to +3, and also the coordination number increases from +4 to +6. So we have previously determined already the oxidation number of iridium here, which is +1. So here the oxidation number of iridium is +3 because the chloroligand counts as an anionic ligand. The bromo ligand is an anionic ligand, and the methyl group is also an anionic ligand when we assign both the electrons here to the CH3 group. So overall, the complex is again neutral, and that means that, well, the iridium must compensate the 3 negative charges fully, and therefore has a +3 charge. Okay, now let's go to the third example, which is a dinuclear addition. And when we have a dinuclear addition, then our reactant has a metal-metal bond that gets cleaved upon the oxidative addition. So you see here the dicobalt octacarbonyl, to which we add H2. Now the H2 adds to the 2 cobalt atoms, and as the H2 adds, the cobalt-cobalt bond cleaves, and that gives a cobalt hydrogen bond. So we have 2 of these molecules having 1 cobalt hydrogen bond each. So this is called a dinuclear addition because we have a metal-metal bond here. Okay. We can again verify that this is an oxidative addition. So the coordination number in this case stays the same. However, still the oxidation number increases. So here in this reactant molecule, the oxidation number of the cobalt is 0. That is because all the carbonyl ligands are 0, have a 0 charge. Okay, so therefore the cobalt must also be in the oxidation number, must be neutral in the oxidation number 0. So over here, the cobalt is in the oxidation number -1. That is because when we assign both of these electrons to the hydrogen, we have a hydrido ligand. And because this is overall a neutral molecule, the cobalt must have the oxidation number +1. Okay, now let us go from the oxidative addition to the reductive elimination. Yeah, from 0 to 1. Oh, sorry, I forgot something. There's another type of oxidative addition, and that's the oxidative addition with intact ligands. So in the previous examples, our molecule that was added was always added under the cleavage of bonds within the molecule. However, that is not always the case. In some cases, the ligands can also remain intact, and that is especially the case when they have multiple bonds. So for instance, when we have alkenes that have carbon-carbon double bonds, alkynes that have carbon-carbon triple bonds, O2 that has an oxygen-oxygen double bond, and so forth. Okay, so in this case, when these ligands add, they do not lose their integrity. They do not break apart, but the bond order within the pi bonds will be reduced. So what's an example for this? The example for this is this oxidative addition of the twist triphenylphosphine platinum. Sorry, to this diphenylacetylene to this twist triphenylphosphine. So in this case, we bind the alkyne side on to the platinum, and then the bond order in the alkyne is reduced from a triple bond to a double bond. Okay? And basically the electrons in the third bond are being now used to make 2 carbon platinum bonds. So in this case, there is again a change in the coordination number from 3 to 4. We obviously add a ligand, but is there also an oxidation? Let us verify this. So in this compound here, in this twist triphenyl phosphine, the platinum has the oxidation number 0. As we add the ligand, the platinum has the oxidation number +2. This is because we consider these 2 platinum carbon bonds single bonds, and if we assign both these 2 electrons and these 2 electrons to this carbon and that carbon here, then both of these carbons get a 1- charge, and that 1- on these overall 2 negative charges must be compensated by platinum, which has a 2+ charge. All right, so in this case, we go from platinum 0 to platinum 2. Okay, but now let's really go to the reductive eliminations. So the reductive elimination is the reverse of the oxidative addition. So what are examples for that? Well, first of all, this requires the reactive ligands to be in the cis position, because otherwise the reaction is not reversible. So when you have an oxidative addition, and that's a trans addition, then the reverse reaction is actually prohibited. And that's because the 2 ligands are too far away. So only when you have the ligand in cis position, then they're actually close enough together so that they can leave. All right, now here's the example. So we have here again our iridium complex, now in the oxidation state +3. The iridium here has 1 carbonyl ligand, 2 twist triphenylphosphine ligands and one chloro ligand. Okay, so therefore the oxidation number is +3. So as the reductive elimination happens, these two hydrogens through molecular vibration come closer together, and through an intermediate transition state, the hydrogen-hydrogen bond can form, and eventually hydrogen will be eliminated, and then the iridium is in the oxidation state number 1, because we have only one inorganic ligand left here. So in this case, also the the coordination number changes from coordination number 6 to coordination number 4. Okay. One application of oxidative additions and reductive eliminations are the catalytic deuteration of benzene. The per-deuterated benzene is an important solvent in a mass spectroscopy, and one can industrially make it using an organometallic catalyst, actually this one here, through a series of oxidative additions and reductive eliminations. So that will overall add 3 D2 molecules to the benzene and eliminate 3 H2 molecules from the benzene as well. So now how does this work mechanistically? So we start here from this this catalyst, and this catalyst is actually pre-catalyst. And that pre-catalyst can turn into the exact catalyst through the loss of H2. And that represents reductive elimination, because over here, the tantalum is in the oxidation state +5. That is because we have 3 hydridoligands, which are negative, and 2 cyclopentadienyl ligands, which are negative as well. After the reaction, we still have our 2 cyclopentadienyl ligands, but only 1 hydridoligand. So therefore, we have many ligands. So we have eliminated H2, and our tantalum is now only in the oxidation state +3. All right. So this is here the reductive elimination. There's actually a chemical equilibrium between the pre-catalyst and the catalyst. When we add H2, then through an oxidative addition, we form the pre-catalyst back. All right. So now how does the catalytic cycle work? We start here out from this pre-catalyst and add benzene in an oxidative addition reaction. So that adds, this phenyl ring, but it also adds 1 additional hydridoligand, because 1 carbon-hydrogen bond within the benzene is actually being cleaved. So we can verify that this is an oxidative addition by seeing that, here we have now more ligands than over here. And here again, we also have a higher oxidation number. So while here we have tantalum in the oxidation state +3, we have here tantalum again in the oxidation state +5. Why? Because the phenyl ring counts as an anionic ligand with a 1- charge. We cleave this tantalum carbon bond. Heteroleptically, the 2 hydride ligands have an anionic one negative charge each, and the cyclopentadienyl rings also have one minus charge each. Okay, so from this molecule, then we can eliminate H2 in a reductive elimination reaction. So these two hydrogen atoms, which are in a cis position, can get eliminated to form this molecule here. And this molecule here has less many ligands, a lower coordination number, and it has again the tantalum in the oxidation state +1 only. So in the next step, we can now add D2 in an oxidative additional reaction. So as we add D2, again, we go from the coordination number 3 to the coordination number 5. And we go from the oxidation number 3 to the oxidation number 5. Okay, so now, in the last step, we can do a reductive elimination in which we eliminate the deuterated benzene. And that produces our catalyst again, and the catalytic cycle can restart. And it can go on until eventually all the hydrogens are substituted by deuterium. Of course, the reverse reaction is also possible, so we must provide actually deuterium in a significant excess in order to make the reaction practically complete. Okay, so now let's go to the nucleophilic displacement reaction. So in the nucleophilic displacement reaction, we add ligands, but we do not add electrons. Yeah. So typically, an anion acts as a nucleophile and adds a ligand. So one important organometallic compound that undergoes nucleophilic displacement reactions is the Coleman's reagent. So this is iron tetracarbonylate 2-. So that can add an electrophile, for example, an alkyl halogenide, to produce this molecule here, which has added the rest R. So in this case, we see that we have added a ligand, but we actually have not added electrons. Therefore, the oxidation number is actually the same. So now the utility of this reaction is that, well, we convert an electrophile into a nucleophile, because similar to a Grignard reaction, in this molecule here, the delta plus is on the rest R and the delta minus is on the halogenide atom, while here it's reverse. Here the delta plus is on the iron and the delta minus is on the rest R. So for that reason, we can perform various reactions that gives us new organic molecules. So in the most simple case, we can just add an H+, and that gives them a simple alkane. So can actually reduce an alkyl halide to an alkane this way. So if you add O2, then you can just oxidize the carbon here, which is attached to the iron, and make a carboxylic acid. If you add another alkyl halide, then we add another rest R. However, this also has to happen in the presence of oxygen, because otherwise we could not insert this carbonyl group here. So last but not least, we can also insert carbon monoxide to give this compound over there. And that compound then can be reacted with H+ to give, for instance, an aldehyde. All right, last but not least, you can also add a dihalogen molecule to this nucleophile, and that gives then an acid chloride. So overall, you can see that you can perform a variety of reactions using nucleophilic displacement, which is actually the reaction between these two reagents to give this reagent over there. All right. One more thing I forgot. You can also react this common reagent not only with an alkyl halide, but also with an acyl chloride as an electrophile, and then you can go to this molecule here directly. Okay, so now let's go to the next reaction, which is called the migratory insertion. And in this case, we have usually anionic ligand and an unsaturated ligand, whereby the unsaturated ligand inserts into the bond between the anionic ligand and the metal. Okay. So you see this principle here. So you have here a neutral ligand, and here you have an anionic ligand, and these have to be in cis position relative to each other, because otherwise the insertion cannot take place. And as the insertion happens, the neutral ligand moves in between the metal anionic ligand bond, and that produces then a new anionic ligand and vacancy. So this reaction is typically an equilibrium reaction, so need actually special tricks to drive the reaction far to the right side. So what are examples for ligands? So X can be, for instance, the neutral ligand can be, for instance, the carbonyl, an olefin on alkyne. It can also be carbene. It can be oxygen, CO2, or a nitrile. And the anionic ligand can be, for instance, a hydride ligand, an alkyl ligand, an arrow ligand, an alkoxide ligand, or an amido ligand. Okay, so here are a few illustrations for this. So here you have so-called carbonyl migratory insertion. And when you have that, then the neutral unsaturated ligand is carbonyl. And upon insertion, the anionic ligand is extended by one carbon, in particular a carbonyl group. Okay. So the carbonyl group inserts into manganese carbon bond to form, in this case, this acetyl group, and you see here this vacant site. So this is an equilibrium reaction, as I said before. So you actually have to add an additional ligand in order to drive the chemical reaction to the right side, and then that additional ligand can occupy the vacant site. Okay. Another kind of migratory insertion is the olefin insertion. So in this case, the neutral unsaturated ligand is an olefin, and the anionic ligand can be, for instance, a hydridoligand. So in this case, the neutral ligand inserts in between the metal and the hydrogen, and then that forms an alkyl group. So the reverse reaction is called the beta-hydride elimination, because a beta hydrogen is being eliminated from the alkyl group. So in this example, it's this hydrogen here. Why is this a beta hydrogen? Because in this case, our alkyl group has two carbon atoms. The carbon atom attached to the metal is called the alpha carbon, and the second carbon atom is called then the beta carbon, and the respective hydrogen is then a beta hydrogen, which gets eliminated in the reverse reaction. So this beta hydride elimination is actually the reason for the instability of many alcohol complexes. So for instance, this platinum complex with two triphenylphosphine units and two butyl groups is unstable. So why is it unstable? Because it can undergo beta hydride elimination. So they are beta hydrogens because we have, well, beta carbons. Okay, this is the alpha carbon, that's the beta carbon, that's the alpha carbon, that's the beta carbon, and we have hydrogens attached to the beta carbons. So therefore, these hydrogens can become reactive toward the metal. Yeah. So the hydrogen here occupies a vacant site, which is actually produced by the statistical loss of the triphenylphosphine ligand. And the hydride unit moves over there to the platinum, and the platinum carbon bond moves over there in order to make carbon-carbon double bond. Okay, now the result is that, well, we have here now an olefin binding side on, and that olefin is now a volatile olefin. So if you do not close your bottle completely, it can statistically detach from the platinum and just leave your bottle. Even though this is actually an equilibrium reaction, because we slowly remove this alkene from the chemical equilibrium, your compound over the time decomposes. Okay, in contrast to that, this molecule here is stable. So here we don't have butyl groups. Here only we have methyl groups. And because we have methyl groups only, we do not have beta carbons, and we do not have beta hydrogen. For that reason, beta hydride elimination cannot happen, and our molecule is stable. All right. So last but not least, there's the carbene migratory insertion. So in this case, we have a metal carbon bond, a metal carbon double bond. And in this case, the unsaturated neutral fragment is the carbene fragment. And that carbene fragment can now insert into, for instance, an alkyl group. And that makes the alkyl group longer. So this alkyl group can then, under circumstances, undergo beta-hydride elimination and produce the olefin here. So this molecule here, again, would not expect it to be very stable because of the possibility to make beta-hydride elimination. All right. So now we have discussed all the reactions. So now let us discuss more closely the applications of these reactions in catalysis. And one important catalyst, the so-called Wilkinson catalyst for hydrogenation reactions. So the pre-catalyst is actually this one here, and you see that we have here rhodium in the oxidation state +1, 3 triphenylphosphine groups, and 1 chloro group. So this molecule can statistically lose phosphine and produce this unsaturated compound in the oxidation number plus in the coordination number 3. So this species here is in chemical equilibrium with its dimer, but this is the actual catalyst. So now this species here can undergo an oxidative addition when we add hydrogen. So that increases the coordination number from 3 to 5 and increases the oxidation number of rhodium from +1 to +3. So this species here is in the in the coordination number 5. It's in chemical equilibrium with this species here, in which we have the coordination number of 6 when we add 1 phosphine ligand. But this is the reactive species that drives the reaction forward. So in the next step, we can add now our olefin, and our olefin can now bind side-on. Get here actually the animations. Bind side-on to this pentacoordinate species to make this octahedral species. And that species can then undergo a migratory insertion. So the carbon-carbon double bond inserts into a rhodium hydrogen bond to make this molecule here with a longer alkyl group. And that species here then can eliminate an alkane to form back the original catalyst. So this closes the catalytic cycle, and the catalytic cycle can begin again until all of the molecules are converted into an alkane. Okay, so yeah, there can also be a side reaction, which I forgot to mention. So this species here can also produce a branched alkane through migratory insertion, because not only this carbon can be bound to hydrogen, a bit to the rhodium, but also this one. That creates this byproduct here, which can then produce this alkene as a byproduct in a beta-hydride elimination. Okay. So a very important application is the Ziegler-Natta polymerization. So the Ziegler-Natta polymerization is widely used in order to make polyethylene and other polymers. So in this case, we have a zirconium catalyst, which is in chemical equilibrium with its pre-catalyst. So statistically, the pre-catalyst is actually a stable molecule. You can lose this chloro group in order to make this species here. And this cationic species here can then add alkene, and that alkene, in this case ethylene, can bind Sidon to the zirconium. So now you see that there's a methyl group next to the ethylene, and now the ethylene group can insert into the zirconium methyl bond. It's a zirconium carbon bond. Okay, so now this gives a longer alkyl chain. In this case, it's made of 3 carbon atoms. And we have here again this vacant site. So now we can add a new ethylene molecule to that vacant site. So again, we have an ethylene molecule close to an alkyl group in cis position. Therefore, again, we can do another migratory insertion, increasing the alkyl chain by another 2 carbon atoms. Now we're having overall 5 carbon atoms. Now you can easily see that this process can continue. We have again here a vacant site. Again, we can add a new ethylene to that vacant site. That ethylene can again undergo migratory insertion, and the chain continues until we have really a polymer. All right. So we have more ethylene, and eventually we have made our polyethylene. So this is the industrial process, how to make polyethylene using a homogeneous catalyst. I should mention there are also heterogeneous catalysts that can undergo Ziegler-Natta polymerization, but the mechanism is far less well understood, as generally the mechanism of heterogeneous catalysis is far harder to investigate than that of homogeneous catalysis. Okay, now let us look at one more industrial reaction. So this is the catalytic olefin hydroformylation. So in this case, you add CO and hydrogen to an alkene using a carbonyl hydride like this to make aldehydes. And these aldehydes can either be linear aldehydes or branched aldehydes in a particular that are obtained in particular ratio, not depending on the reaction conditions. So this reaction requires a high partial pressure of carbon monoxide and hydrogen of about 100 atmospheres. All right, what's the mechanism? So this is actually our actual pre-catalyst, and you see that is our dimeric cobalt carbonyl that we previously discussed when we discussed the carbonyls. And now in the presence of hydrogen, we can do an oxidative addition. And then we form our carbonyl hydride, which is the actual catalyst. So that carbonyl hydride can lose a CO, and we can add an olefin. So this is actually a substitution reaction. So now you see we have this alkene being bound side on to the cobalt. So on the next step, we can just add carbonyl ligand, and we undergo a migratory insertion that inserts this olefin here into the cobalt hydrogen bond to give this species here. Again, there are two possibilities. This carbon can make the bond with cobalt, or this carbon. If it's this carbon, then we get the linear alkyl group, and if it's the other carbon, then we're getting a branched byproduct. Okay, now we can add CO to this species, and then we go to this species here. So this species can again undergo another migratory insertion, but in this case, a carbonyl is actually inserted in the alkyl group. Okay, and in the next step, we then can lose a CO ligand, and we add dihydrogen in the oxidation in an oxidative addition step, and that is actually the slowest reaction step overall. So this gives this group here, and this group can then be eliminated in a reductive elimination step to form the aldehyde, and the catalyst is formed again. Okay, so I think we can stop at this point.